displacement gradient with respect to space. And because the displacement is shape function times normal displacement, so when you take these differentiations, then you can readily find them. Okay, let's try to derive this out by hand. Okay, the displacement at any point, okay, is equal to u1 n1 plus u2 n2. Okay, where the u1, u2, okay, they are interpolated by two different shape functions. This is your n1x is equal to 1 minus x over m. The other is the n2 is equal to x over m. Okay. And then next, what we're going to calculate now is, in the case of total potential energy, you have the strain energy minus the work done. The work done by the F1, F2. Potential energy got to be changed when this rod is being heated. Previously, the potential energy is defined as stress, strength, ED. This mechanical stress, strength, area depends. Mechanical stress is defined as Young modulus times the strain. Okay, but this is your mechanical strength. But in our calculation now, this mechanical strength is the total strength minus the thermal strength. Okay. What you do in the calculations U is your total displacement. It's due to the one that was caused by the cooling, the expansion due to the cooling, and alpha delta T that is caused by the thermal expansion. Okay? So you got to do the correction here. Okay? So for the simplification, I write this epsilon to be total. This one to be the thermal strength. Okay? Now let's come back to your total mechanical strength energy. It's going to be written as Young modulus, the strain minus the thermal strain, and the strain minus the thermal strain. A dx. Okay? And this expansion is quite straightforward one. You have the EA and then total strain square minus 2 times total strain and strain plus strain square. Okay? So this is what you have. And now, back to our list of potential energy. How do you derive the force? To find the force balance, you have partial differentiations of the total potential energy with U1. The minus, what's that force? Your force is your F1 times 1, and then the other term are 0. So this is the way you find the force expression. F1 is equal to del UE del U1. Okay? So let's see how can you obtain this. Okay, this is a bit complicated, okay, because this is epsilon. Okay? What happens if you can do the expression here? Your strain energy is what? du dx. Then it is going to be dN1 dx U1 plus dN2 dx U2. Okay? So if you now go to do the differentiation, okay, you're going to, okay, this divided by half, this is the EA divided by half, and then 2 epsilon, and then the epsilon du. Okay? So this proved to be quite a troublesome one. Okay, let's see. Okay, you see here, if you want to do this, then you need to do the partial differentiation. Okay, converting these expressions into these. Okay? Let's see how is it there. Okay, we handle one by one. Okay, thermal strain, we check the expression here. Okay, the epsilon dt. Okay, epsilon is the n1 dx u1 plus the n2 dx u2. So what is your the epsilon du? Let's say you take the epsilon, the u1, then this is the n1 dx. Plus something times 0. And then your the epsilon du2 is equal to 0 plus the n2 dx times du2 du2. This is equal to 1. And then what about the epsilon t? Epsilon t is alpha delta t. It's a constant. So if you know the epsilon t du, then it's 0. So in this case, the last term is 0. Second term is the yeah, space functions. It is the n, the x. Okay, which variable depend on which shape function depend on which displacement you're taking. And this one you can do the expansions. It is 2 times the n1 dx u1 plus the n2 dx u2 times this is what? This is the ni dx. Okay. So with this, now you can write your 2 equations. Okay, let's first write the first equation. The first equation is going to be f1 is equal to del u e del u1. Okay? So your expression here is 2 times EA over 2. Then you have the EA, the integral of the first term is your the n1 dx u1 plus the n2 dx u2 times the n1 dx. How about the second term? The second term is your minus the n1 dx times your thermal strength. Okay? And then dx. Okay. So this one, later we're going to handle. Okay, but we can still do the separation first. First term, we're going to have the n1 dx square u1 plus the n1 dx times the n2 dx u2 and then dx. Okay, this is the first term, and then the next term is your minus EA and then your integrations of the n1 dx dx. Okay, so this term got special meaning. If we bring it to the left hand side, EA epsilon t, what is this? This is n1, x equal to 0, x equal to L. Okay? So your expression here now become f1. F1 happen to have n1 is 1. Okay? Is it 1? This is plus E A alpha delta t at n1 at x equal to L minus n1 at x equal to 0. Okay? So what this is on the left hand side? this is equal to 0 or N1. This is equal to 1. So the first force term is F1 minus EA alpha delta T. Okay, so this is effectively the thermal forces. It's equal to your expression here, EA. Okay, if you now write that in the matrix form, I'm going to have EA times L, because this is all going to be constant. This is 1 minus x over L after differentiations. Then you have the minus 1 over L. Okay. So anyway, we write it first, then you do the integration later. The same analysis, you can repeat it here. You're going to have F2, but then you're going to have the subtraction of N2 minus N2 and not 2 and not 1. Then you have the positive EA alpha delta T. And then this one, you do the same. You're going to have dN1 dx times dN2 dx. And finally, the last term will be dN2 dx squared. Okay. So in the end, you are obtaining the same expression as we did. But this time around, we are using the structural analysis, total potential energy method. Okay, so this is the working. Okay? Eventually, you now have an expression here. And then, in the end, you have the EA over L. Yeah. But I think our working is clearer from the mechanics point of view. From today one, copy down. In the case of the, if you're treating finite as a software, this might not bother you. But if you want to apply it to other fields or different boundary conditions, so you really have to understand the basic, okay? Because they might cause some difference, okay? So, where do you find this useful? Indeed, even though this is a thermal strength simulation, but it can be applied for actuator design. Imagine if you are now handling piezoelectric actuator, you are handling some pneumatic actuator, you want to simulate the effect of elongation by applying induced strength, then you will apply this. Okay? So how do we read this Now, the first two terms is still the Hooke's law, but the introduction of the thermal expansion is effectively like stretching a rod by extra thermally induced force. Okay? If you are not talking about thermally induced strength, you are talking about piezo induced strength, then you can also do the same. But piezo induced strength depends on polarity. It could be thermally induced compressions. Then this is a thermally induced compressive force rather than the tension. Okay? So in summary, you can write what we did in this matrix form. The elastic strain is the matrix times the total displacement minus the thermally induced strength. Okay? This B matrix is what you call the differentiations of the displacement with respect to the space. Okay? And then next, what is the stress? Stress is the Young modulus times the mechanical strength. And what is mechanical strength? Mechanical strength is the total strength minus the thermally induced strength. Okay? And then next, what is the elastic strain energy per volume? It's just half the stress times strain, or you can express it as half times Young modulus times the net mechanical strength squared. If you do the expansion, you can also write them in the matrix form like this: E, U, B, transpose minus the thermally strength is the scalar times the B matrix times Q minus the scalar. Okay? So our operation beforehand now can be done in the matrix form. Okay? But it's just kind of a re-expression only. So you can do this operation by matrix. Okay? The first derivative with respect to displacement U1, okay, will give you the first row being non-zero. Okay? And then the rest is the B matrix multiplication with the rest. And if you do the same, then you will eventually find F2. So next, then we also try to tell you about thermal stress. Okay? Thermal stress is, you know about thermal expansion. The actual stress, actual mechanical stress is the modulus times the net mechanical strength, that is the total strength minus the thermal strength. Okay? So, how to write the Galvin equation for the rod subjected to heating? So, to do so, you do the same force balance on one single element. You can find the stress chain with space is 0. But this time round, the stress is equal to net mechanical strength. Okay? So supposedly, if you do the substitutions of this total strength is du dt, then you are going to obtain the equations which is second order derivative of displacement plus a strain term. If the strain is varying along the length, then this term is non-zero. But for finite element simulation, you usually assume constant strain throughout the element. Okay? So this is a sort of the simplifications. Okay? So yeah, you'll be checked. Yeah. Is this assumption of constant strength valid? Yeah, it's only valid when your mesh is very fine. You have a very small division of the rod into small pieces. Then this is valid. If your rod is too long and your temperature is different, then it cannot be true. Okay, take an example. How do you model a rod between hot and cold surface? So imagine you have a hot wall and you have a cold wall. In between them, you have a rod Okay? If you only have one single element, so this assumption is wrong. Because temperature distribution is hot to cold. Okay? Your strain, okay, your strain is, thermal strain is alpha delta T, and then times the length, let's say dx. Okay? Then if you now our length, okay, then if you now have your these expressions, okay, if temperature is now a linear function, okay, let's see. Okay, this strain, that's fine. Okay, so small dx. But if these T delta T can be expressed as N1 pH plus N2 T cold minus the reference temperature, then the epsilon T dx is never 0. Okay? Because of the spatial temperature distribution. Okay? You see that? Yeah. Don't get arbitrary assumption, even though you can do it by fine measures, but you will not be right. Okay? When you have a couple temperature and thermal and elastic loading. Okay? So these assumptions is not valid. Okay?
Well, 0 when the temperature is constant, right?
Yeah. So what you did is you have to impose stepwise constant, but then you got to apply the right temperature. Okay. I think this was also one of the past questions before. Okay. I don't go so many elements. I only go 2. Okay. Rather than going 4, I go 2. Okay. Are you able to do the right assumption? Okay, that's important. Okay. You can do stepwise constant. So one hot, one cold for 2 elements. You can take the average temperature T hot plus T cold divided by 2. Okay? That 2 solutions should converge to 1 solution. So that's the importance of finite element. Finite element, when you find the mesh, the solution must converge. If it diverge, something is wrong. Okay? Okay, now also the block force and block stress, yeah, we have covered this before. Okay, now is, okay, can you do the same formulations by means of Gallatin method? Okay, this is what we're going to do now. Okay, we have go through structural analysis, Hooke's law, to find out what is the effect of thermally induced extensions. We also have used the total potential energy. The last bit now is to do with this Gallatin method. Okay? So here, Gallatin method is almost exactly the same as you did. Okay? But here, what you have to find out is substitution of the total strength into the expression above. Okay? du dx in the presence of thermal expansions is total strength. This total strength is the sum of mechanical stress induced strain plus the thermal strength. So you can see that when you substitute this expression into galactic method, nothing is really changed a lot. What is changing is your right hand side. Your right hand side get area times mechanical stress times the straight function. Its straight function is 1 at x equal to 0, this will be 1. Then your expression here is minus a sigma. Okay? The straight function is 2, it is non-zero or 1 at x equal to L. Then it will be positive a not too stress. So not too stress, which is the stress on the right hand side is positive, and the stress on the left hand side is negative for pure tension. Okay. Likewise, for this case, then it's simply this the mechanical induced strength. Okay. So you can see that for straight function 1, your mechanical induced force is negative. For straight function 2, mechanical induced force is positive. Okay. So with this, if you are using galactic method, you're still going to obtain the same expression for the stiffness matrix times displacement vector. The right hand side consists of 2 parts. One is the pure mechanical force F1, F2, which is defined to be positive toward the right. Okay, but the thermally induced force is imposing a tension. So they are positive on the right, negative on the left. Okay, so this is what we do. And then next, when you look at the example, consider you have a rod which was clamped at both ends, and this rod are subjected to temperature rise. We'll be able to find out what's the reaction at the dead end, and given the rod made of the material with a Young modulus of 206.8 gigapascal and the thermal expansion coefficient of 12.6 times 10 to the power of -6 degrees Celsius, the cross-sectional area of 2,580 millimeters square, and a length of 1.2 meters. So in this analysis, you're going to have 2 reaction force, one on the left bow and one on the right bow, F1 and F3. And then, so what's next? The only free end is not 2. Not 1 and not 3 are all fixed. Let's write the element 1 by 1. You have the element 1, U1, U2 times the stiffness matrix is equal to the force vector plus thermally induced force. So in this case, your force vector is non-zero on the left hand side. This is the reaction force. At the middle, because you impose of no external force, is 0. It's going to 0. And then on the right hand side, then you have these thermally induced tensions. How about the element 2? For the element 2, it is a displacement of U2, U3. This displacement vector is multiplied by a stiffness matrix. Is equal to the force sum. This force sum has a non-zero external force at the log 3. There's a reaction force at 3 plus the thermally induced force, which are the tensions. By doing the sum of the forces, we have F1 from the left reaction, F3 from the right reaction, and these force, thermally induced force on the left element and thermally induced force on the right element, you've got to do the sum up. So what you can find out, when you sum up this, then you're only left with the tension in the outer bar. So this force sum is equal to the stiffness matrix times displacement vector. So, but because two displacements are fixed, okay. So now you can handle one of the equations. Let's write it down. Okay, after you have written this, you find that you only need to solve equation 2. And it turns out equation 2 is 0. And since equation 2 is 0, then you can do the substitution back to equation 1 and 3. So that you can find out what is the reaction force. And then the reaction force divided by the cross-sectional area will give you the axial stress. Okay? Okay, I think with this, then we are done for today. Then please go back and try out. I will post the homework, then you can try out. And then for next week, then we shall have these NCs hands-on sessions in the computing lab. At the same time, I will ask you to do to form a different grouping, because in this assignment we're going to do the analysis of the 3D truss. Okay. This 3D truss will later be used as your smartphone later. Okay. You're going to drop your smartphone in a carrier with legs. Okay, so that will be the final project we're going to do. But as for today, we only take care of one leg made of the 3D truss. As for the ladder, okay. So yeah, you can start forming your group. Okay, we have how many students? I think 40 plus. So I'm suggesting you guys to divide yourself into nine groups. Each group have about five students. Okay. Yeah. So what I will do, simple one is, we have your class list, and then I will follow your class list. Okay. Group 1 to 9. Okay. First 9 person divided into 3 groups, into 9 groups. Okay, let's see your class list. So there will be even out so that you have. Okay. Let's see as your. Okay, your TA, there will be big TA.